All right, so this is going to be a pretty high level broad overview and introduction to reverse engineering. So if you already have reverse engineering experience, most of this information is probably going to be redundant. So uh, just bear with me if you're in that category. But if you're brand new to reverse engineering or to cybersecurity in general, this talk is for you. It'll help you kind of understand the control flow, what reverse engineering can be used for, and how you can get started. So just a brief overview of what reverse engineering is. It's basically just taking some program or system and analyzing it. So that could involve tearing it down. So like if it's a hardware system, you could be physically taking it apart. Or if it's a program or a binary, you can be disassembling it to its source code, so it's assembly level instructions. So in the context of this talk and usually cybersecurity, usually reverse engineering refers to that latter topic, which is taking that compiled executable, then disassembling it with a tool called a disassembler, and then analyzing the assembly code. And you can also run that assembly code or run the executable. So reverse engineering is also commonly referred to as black box analysis because sometimes you don't know anything about the system you're reverse engineering. So you just know it takes some inputs and it produces some outputs. Normally you have more information than that, but sometimes you don't. So that's where you get that nickname black box analysis, because you're given like a black box. You don't know what's inside of it. You don't know what the program does, and it's your job to figure it out. So reverse engineering typically consists of two phases, static analysis and dynamic analysis. So the disassembling and analyzing of the assembly code, that's static analysis, because you're looking at the program, trying to understand its control flow without actually running the program. Dynamic analysis, you're actually executing the program and you're trying to figure out the behavior of the program while it's running. So the main difference is just, is the program running, or are you looking at it without it being run? That's the main difference between the two. So there's a lot of different applications of reverse engineering. So I just listed a couple. So one of the biggest and most fun applications of reverse engineering is in the game world. So game mods. So that can constitute making cheats, speed running, adding different mods and content, tricking a server, or bypassing anti-cheat. So all of these things have some element of reverse engineering required to do them. So you can see some really cool things done by a lot of people in the security community, breaking into the game community because they have this reverse engineering background. So that's definitely one of the flashier applications of reverse engineering, because you can physically see like the end result. You can also use reverse engineering to bypass copyright protections. So you can make a key gen to generate keys for a software program that has like a trial version and you need a key to unlock the full version. You can patch software so that way it like removes a watermark that it might put in a video or something like that. Basically, you're just looking at the control flow of a program and then finding those copyright protections and the different checks and then patching them out. You can use reverse engineering to find vulnerabilities in various software libraries, applications, firmware, hardware. And you can also use it for malware. So you can do malware reverse engineering to figure out how different malware samples operate and how they infect and propagate through a network. So these are two examples of people reverse engineering. So the first one, you might have seen this because this was pretty recent, but someone reverse engineered McDonald's API and then made basically a publicly accessible web app that would basically place orders to every every McDonald's across the nation to figure out if the ice cream machine was broken. And then it would report that status back to the user. So you could go to the web app and you could figure out which locations had a broken ice cream machine. And so he had to actually do reverse engineering of network packets and like look at the web traffic and then also look at the source code on McDonald's website to try and find out those API details to do that. So that's a pretty fun application. And then also, like I said before, modding in video games. So I'm just gonna play a little bit of this video. Let me know if you can hear the sound all right or if it's not coming through properly.
When it comes to video games, there's nothing quite as varied and creatively unique as the mod scene, or modification scene if you want to get serious about this. Want Owen Wilson to say wow when you land a critical hit in World of Warcraft? No problem.
Wow. Wow. Wow.
Have an overwhelming desire to explore GTA 4 as Sheriff Woody? Get on it, buddy. Looking to replace everything in Doom with Home Improvement's Tim Allen? That one is a little odd, but here it is. With such talented modders out there and complete freedom at their fingertips, imagination is the only restriction on how wild their creations can be. Becoming a larger community by the day, and let's face it, varying massively in quality, it's becoming increasingly difficult to navigate this vast sea of mods in order to find something worth your valuable time. And trust me, I know that you've got high standards and excellent taste. It's why you're watching Triple Jump content, right? Or perhaps you watch Triple Jump content because we're always on hand to do the hard work for you when it comes to digging out the weird and wonderful from any given gaming treasure trove. Well, guess what? Today is no different, as we're going to have a gander at some of the modding community's more interesting offerings. I'm Peter from Triple Jump, and here are the 10 strangest mods in video games.
Okay, so I think you guys get the picture of like some of the things you can do and create with a background in reverse engineering. The opportunities are pretty endless. Once you get the foundational skills, you can apply it to a lot of different things. So to reverse engineer a program, specifically a software program, typically you need a disassembler or a decompiler or some program that combines the two. So some of the most popular ones out there are IDA-Pro, Radare2, Ghidra, and Binary Ninja. So we're going to be showing Ghidra today. And then debuggers, those are used for the dynamic analysis portion. So they're really good at showing the state of a program at any given time. So you can set breakpoints at a certain moment in the execution of a program, and you can view the states of the registers, you can view the memory, and do all sorts of stuff. So probably the most powerful debugger out there is GDB. It has support for a wide variety of architectures, and it has a lot of features. And it also has a very extensible API, so you can script in Python, or you can actually modify the source code and add your own architecture support. It's very well documented. It's been around for a while. It's pretty much the go-to. There's also additional extensions and plugins you can use with GDB. So if you start branching into binary exploitation and Pwn, there's different plugins you can get, like there's Pwn DBG, there's Jeff, and then I'm blanking on the third that's normally used. OllyDBG and WinBag, or WinDBG, those are two debuggers specifically for Windows. So OllyDBG is more for user space programs, whereas WinBag or WinDBG is really good for kernel level debugging. And then a hex editor is also very useful, especially if you're doing anything with unknown file formats. So you can use a tool like O10 hex editor, and you can make your own template for an unknown file type based on your reverse engineering. So you can figure out, oh, this series of bytes corresponds to a custom file header. This sequence of bytes represents a game map or something like that. And you can actually write up a template, so that way whenever you analyze future files like that, you can apply that template and it'll automatically structure the data in a readable way based on your previous analysis. So O10 hex editor is the most fully featured. You can use free hex editors as well, especially if you're getting started. I would recommend a free hex editor. So that's actually what I use. I use a free one called Hex Editor Neo, and it's pretty good. It's not as fully featured as O10, but it does the job. And then also having some sort of scripting language that you can use to write scripts quickly is invaluable in the reverse engineering process. So Python is usually the go-to, but if you're really good at writing scripts in Perl, like, go for it. You do you. Whatever you can use to quickly script something up and use it to, like, an example would be like crack an MD5 hash. And I'm saying that because that was recently in a reverse engineering CTF challenge. So I'm specifically going to be talking about mainly x86 as an architecture. I'm going to be talking about C programs, and I'm going to be talking about like reverse engineering ELF executables. So in order to understand that, I think the first thing we need to know is how programs are built. So if we have a C or C++ program, some program, this is generally how it's going to be built. So we have a source code file that we wrote. So like program 1, we wrote it for our programming 1 class. So it just prints out hello world, I guess. So the first thing that happens when we try and compile it is the C or C++ preprocessor basically parses your include statements to see what header files it needs to include. And then it will basically copy all of that code from the header files and basically paste it into a bigger body of source code that then gets sent to the compiler. And the preprocessor will also be responsible for expanding macros So this is important in C. It's not used in C++ too much, but macros are just ways to like restructure your code or execute something before it goes to the compiler. And this is really good for optimizations, specifically like memory optimizations. So once it goes through the preprocessor, it'll go to the compiler, and the compiler will compile it down to what's called an assembler file. So it'll apply any optimizations, and it'll translate your C or C++ code, that higher level code that's pretty human readable. It'll translate that into assembly level code. So this isn't as human readable. It's still, like, you can still read it and get a pretty good idea of what the program's doing, but it's not going to be as nice and neat as like C or C++ source code. So this assembler file will then go to an assembler, and the assembler will assemble that source code. So basically making it into object code, which is basically everything except for the object code needed for library functions. So it's pretty much everything that's going to be going into your executable file except for the library function code. And then that object code file will go to your linker. If there's any library functions that need to be linked in, it'll handle that. If it needs to relocate any symbols, it'll do that. So one example of this would be if you're writing a multi-threaded program, you have to link in a special library in order for your program to execute successfully. And that's like the LP thread library, I believe. So those, like that library needs to be linked in, that object code for that library needs to be combined with the object code from your program. And that's handled by the linker. And then once the linker is done with it, you get a fully fledged executable file that you can run on your system. And so we have our prog1, and that's what we would turn in for our assignment. So in the case of x86 and like a Linux environment, that executable file will be an ELF formatted file. On a Windows machine, it would be, you would see like a .exe extension. So that's a PE file. So it's a different file format. So that's why you can't easily run executables that were compiled for Linux or Mac on Windows and vice versa. You need some sort of intermediate program, or you need to cross-compile. It's because they're in different executable file formats. Before we go further, this is just kind of a side note, but it's useful to know. Processors can be either what's called little endian or big endian. So this is really important when it comes to reverse engineering, because when you're looking at memory addresses and like the content stored in memory, you have to know the endianness of your processor architecture, so that way you know how to interpret the memory you're reading. So endianness just means the order of bytes in a given word of memory. So big endian systems store their most significant byte at the smallest memory address, and their least significant byte at the largest. And then little endian systems are the exact opposite. So they store their least significant byte at the smallest address and their most significant at the largest. Most processors are going to be little endian, and so most processor architectures are going to be little endian. Most network protocols, however, are big endian. So that just something useful to know. So if you're writing some sort of network client or server, you often have to take this into account and have to use certain functions that translate for the different endianness. So that's just a side note. It will help us later when we're looking at a disassembled program. And then this is just kind of further emphasizing that. So if we have some data 01, 02, 03, 04 in hex, if we have that data, if it's being stored in memory on a little endian system, it'll be stored as 04, 03, 02, 01. And then big endian is the opposite. So you can kind of see the difference between the two. So big endian, it would just remain the same. It would just be 01, 02, 03, 04. But little endian, you would have to actually switch all of the bytes. So it's just changing the order. It's not actually changing the data, it's just changing the order in which that data is stored. So like I said, we're going to be focusing on x86. So that's one of the most common assembly languages, and it's used for pretty much all like modern programming, like Windows, Linux, Mac, they all have support for x86. It's one of the most well-known and common assembly languages. Most compilers are made for x86, so compiling some source language down to x86. x86 has a 32-bit version and a 64-bit version. So if you are on a Windows machine, you may have noticed in the past that there's two different program files folders. So program files and program files x86. This is because of the difference in versions, the 32-bit versus 64-bit. So programs that use the 32-bit are installed in program files x86, and program files that use the 64-bit are in program files. So that's just kind of a side note. x86 has two different syntax flavors, so Intel and AT&T. So they have some minor differences. Mainly, like the biggest difference is operand ordering. So like the source operand and the destination operand are switched between Intel and AT&T. So that's something that's really useful to know when you're looking at x86 instructions, trying to figure out if you're looking at Intel or AT&T. And it's pretty obvious which one is which, because AT&T has prefixes and suffixes. So like AT&T will have a suffix on instructions. So like the move instruction will have a suffix indicating the operand size. So it'll be like move W, which indicates you're moving a word. And then it also has prefixes for registers and then immediates. I don't remember exact suffixes exact prefixes off the top of my head, but when you're looking at them side by side, it's fairly easy to tell which is which because AT&T is the one with the prefixes. Today we're going to be focusing on Intel just because it's a little bit easier to read and figure out what's going on. x86 has 8 general purpose registers, 6 segment registers, and 1 flag register, and then it has an instruction pointer, and we're going to be going into more detail on the next slides on what those things are. So these are the general purpose registers. So they are 32-bit registers in the 32-bit version of x86. We're not going to be really focusing on the 64-bit version today, but it's it's not too hard to apply the same concepts because the 64-bit version of x86 just basically extends these registers and makes them 64-bit, and you can reference the 32-bit portion of it if you just want the lower 32 bits. You can also reference the lower 16 bits by referencing AX, BX, CX, and DX. You can reference the upper 8 bits of AX with AH, upper 8 bits of BX with BH, upper 8 bits of CX with CH, upper 8 bits of DX with DH, and you can also get the lower bits with AL, BL, CL, and DL. So EAX, EBX, ECX, and EDX are generally used for storing data, moving data, basically whatever operation where you need to temporarily put data in a register. Those 4 are generally the ones that are used. That being said, those registers also have common purposes aside from that. So EAX generally is used to store the return value from a function. And we'll show that in some assembly, so you know what I mean by that. EBX will often store a base pointer to the data section. ECX often will act as a counter for like strings and loops. EDX, I guess it can be used as an IO pointer. ESI stands for source index or source pointer, and then it paired with EDI, the destination pointer or destination index. Those are used for string operations or some batch operations. So like if you're copying a amount of data, so like memcopy, that C function, they would be using on the assembly level ESI and EDI. So with memcopy, you have a source pointer and you have a destination pointer because you're copying some memory from one memory address into another. Usually it's for strings. Usually you're copying the data that represents one string into like you're copying it to a memory address mentioned by the destination pointer. So that's kind of what the ESI and EDI registers are normally used for. ESP is the stack pointer. So it will always point to the top of the stack. So I'm gonna show a diagram of the stack in x86, and I'm gonna explain what the stack does, what it is, why we use it. But basically, the stack is a data structure used for memory. And I'll go into more detail when we talk more about the stack and ESP. EBP is the stack frame base pointer. It's also called the frame pointer. So you may see it referred to as base pointer or frame pointer. They both mean EBP. And then EIP is the instruction pointer. So it just points to the next instruction to be executed when you're running a program. It can also sometimes be called the program counter. So both instruction pointer and program counter usually are referring to that EIP register. And then this isn't as important as what we just went over, but it's useful to just kind of have in mind. The segment registers, specifically CS, DS, and SS, they're just pointers to different segments that your program uses. So CS points to the code segment. So that's like pointing to the instructions that your program actually uses for execution. DS is for the data segment, so all data that your program accesses, and then SS pointer to the stack. And then you have 3 other segment registers that you can use for other addressing. So you can use it for like addressing if you have additional memory, like video memory. Then also there's something called an E-flags register. So these flags, some of these flags get set on certain operations. So like when you're running an instruction, some of these bits may get set from 0 to 1 to indicate that that condition is true. So usually the most useful ones to pay attention to are the carry flag and the 0 flag, depending on what you're doing, but the 0 flag is often used for comparisons. So when you're comparing 2 variables or 2 integers, you're comparing 2 things. The 0 flag will get set to indicate one way or another if they're equal or not. So that's something to pay attention to, because comparison operations in the background, they do a subtraction operation. So if one value subtracted from the other equals 0, then those 2 numbers are equal. Those 2 variables are equal, and that 0 flag would get set. The carry flag would get set on arithmetic operations. So if there was 2 numbers getting added, and so like 2 16-bit numbers getting added, and you have a 1 in the 17th bit. Well, you can't represent that in a 16-bit number. So you have to set a carry flag to indicate that there is some sort of overflow, like there is a carry in that arithmetic operation. All right, sorry, I'm just gonna catch up on the chat real quick. All right, Zoom is not pulling up the chat for me. So if you guys have any questions, feel free to shout them out right now, because for whatever reason, I am not able to view the chat. I'm gonna just pause my sharing and see if that, okay. Okay. All right, yeah, thanks, Owen. Sorry I'm a little late to addressing the comments in the chat, but yeah, the third extension for GDB is PEDA, P-E-D-A, and so I was just blanking on it. So thanks, Owen, for posting that in the chat. And then also regarding game modding, like Scott said, for certain programs, they don't care. Like certain games, they encourage modding. In other games, they will openly prosecute modding. So it's very much what are the terms and conditions of this game, and what is the attitude of the developers to community modding. So when in doubt, don't post mods anywhere. If you just develop mods for your own personal use and don't use them, like if you just use it for like a single player local game on your computer, you're generally going to be fine. But if you do it for a multiplayer game, where there's some server you're interacting with, you're moving into a gray area. You could potentially be running into issues. With that being said, I'm going to go back to more x86 basics, talking about addressing modes. So there's multiple different ways to refer to or address memory or data of some sort. So the first type is called register addressing. So basically you're just moving the contents of one register into another. You're just copying that data from one register into the other. So in this example, you're moving the contents of BX into AX. So that's pretty straightforward, pretty simple. For immediate addressing, you're moving an immediate value. So that's some constant, some number or some data that isn't stored in a register. It's not stored at a memory address necessarily. You're storing the immediate representation of that data into a register. So you're moving like a decimal number, or you're moving a hex number directly into a register. You're not fetching something from memory and then moving it. The next type is direct memory addressing. So this would be if you wanted to move some number or some data value from memory into a register. So like, let's say you have some variable 0, well, it's in hex, so ABCD, hex ABCD, and that's your variable. And you want to copy that, the data of my var into AX. The way you would do it is you do move AX, comma, and then in square brackets, my var. And this is all in Intel syntax, by the way, because Intel syntax uses square brackets, AT&T uses parentheses. Direct offset addressing, basically it's pretty similar to direct memory addressing, but instead of just having a variable that you're trying to access, you're trying to access some offset of the start of the variable. So like, let's say you have, in this case, it's a table of bytes, and you want to address, you want to get the second offset. So you want to get the this is the start, and then you want to get +2. So you want to get the start plus 2 bytes. So that's basically what that type of addressing is referencing. So you would do move AL, then byte table +2. And so if we remember, AL is 8 bits, so we're only getting the lowest byte here. Register indirect. So basically it's just getting the address that's stored in a register, and then accessing the data at that address, and then moving it into AX in this example. And so this can only be used with a couple specific registers. So you can only use it with BX, BP, SI, and DI. So I said earlier we were going to talk about the stack, and lo and behold, here's the stack. It's what's called a last in, first out data structure. So if you talked about this in programming 2 or data structures, you're generally familiar. You have a good understanding of what I mean by last in, first out. So like you can think of it like a stack of plates. So like when you're putting something onto the stack of plates, you're putting a new plate on. You put it on the top of the stack. When you're removing an element from that stack of plates, you take an element from the top of the stack. So everything is either being added to the top or taken from the top. So that's what last in, first out is referring to. So the stack for x86, it operates the same way. And the stack is a memory structure. It's used to store information that the program needs during the execution of the program. So this includes local variables and parameters, function return addresses, and a lot more. So it's basically just used to maintain the state of a program and help keep control flow logical and store values. So if you wanted to dynamically allocate memory, so like if you have a variable that you don't know what size it will be at compile time, then you have to use something like malloc or new. That is not going to be stored on the stack. That's going to be stored on the heap because you don't know the size. That's going to be what's called dynamic memory. So it has to dynamically allocate it, and the process of memory allocation is much different for dynamic memory versus memory where you already know the size. So if you're familiar with stacks, we push data onto the top of the stack and we pop data off the top of the stack. So we're using push and pop operations. And then this is kind of the one major difference from a data structures stack that you learn in one of your classes and x86. The stack grows downwards. So when you're adding things to it, it's growing downwards from high addresses to low addresses. So when you're first adding things to the stack, that's going to be the highest address that you reference. And then as you continue to add things, it's going to decrement the addresses. And so it's growing downwards. And then that can kind of be seen in this image on the right. So as we add things, it goes from high to low. And it's, okay, so this one, the higher addresses are at the bottom and they're having it grow towards the top. It's basically the same thing. It's just they flipped it. So that's where it can get kind of confusing. So just remember, the stack grows from high addresses to low addresses. As long as you remember that phrase, you'll be able to deal with the differences in diagrams, because each diagram is going to be different. They're going to draw the stack growing in different directions, but it's always from high to low. So with the stack, we're going to talk about how functions maintain their control flow. So when you're calling a function, there's both a caller and a callee. So the caller has certain responsibilities that it needs to do, and then the callee also has different responsibilities that it needs to do. So when I say caller and callee, you can think of like main, the main function calls some other function, let's say foo. So main calls foo. Main is the caller, and then foo is the callee. So they each have something they need to do to maintain the stack and maintain the program state. So main, in this case, would need to save the contents of the EAX register, the ECX register, and the EDX register. And the reason why it needs to save these, the contents of these registers is because they could change in the function it's calling, the subroutine it's calling. So you're saving the contents by pushing those registers, pushing the content of those registers onto the stack. And then if there's any parameters associated with the subroutine, those also will get pushed onto the stack. So when they say parameters, it's like parameters or arguments, whichever helps you understand what they're referring to. So like if foo has 3 parameters, like x, y, and z, and they're all integers, those have to be pushed onto the stack. You may not know what x, y, and z are, but you need to have the space allocated on the stack. Then the subroutine needs to be called. So the caller will place the return address on the stack and then branch to the subroutine code. So in this diagram on the right-hand side, for those 3 things, it doesn't show saving the contents of EAX, ECX, and EDX, but they would be right here. And if you notice, they're at positive offsets from the base pointer. So the second thing that it's doing, passing the parameters and pushing them onto the stack, that's happening here. And then it's in inverse order. So parameter 3 gets pushed before parameter 2, which gets pushed before parameter 1. And then the return address also gets pushed onto the stack. So that's that lets the program know that when I'm done executing foo, I know where to return. I know what to set my instruction pointer to, so that way I can continue execution. I can go to the instruction right after the call to foo, and I can continue the flow of my program. And then this is after a subroutine has finished and the callee has returned the context back to the caller. The caller has to remove parameters from the stack. So it has to remove these 3 things from the stack, and it has to restore the content of those saved registers. So it has to pop them off the stack. So that would be down here if they chose to include it in the diagram. So the callee, so this would be what foo has to do, not what main has to do. Foo would have to push the value of the base pointer onto the stack because the base pointer is going to change. So it needs to have the base pointer on there, and then it's copying the value of the current stack pointer into the base pointer. So I know that's kind of confusing for individuals who.
Claire?
Okay.
Is your screen share still paused?
Oh, it's still paused. I didn't realize. All right, here. Let me go back. So yeah. So this was the slide with stack information. Did you guys see the addressing modes? How long was it paused for?
For a little while.
Okay. I am very sorry about that. Are there any things that I talked about that were confusing because you didn't have the slides? So I'll go through really briefly and show the slides for what I was talking about.
You were paused in the addressing mode. So
Okay.
after that, I think it was mostly when you were discussing a specific diagram, you were, I think, pointing to certain things that we couldn't see. But other than that, I think it was okay. It was just that we were just looking at the same slide.
Okay. So this was the diagram I was referring to while I was talking about Calder and Cawley subroutine steps. So the caller has to save the contents of the EAX, ECX, and EDX register, and that would be right here if the diagram chose to include that, but they didn't choose to represent that. Then if there's any parameters for the foo function, then they would need to be pushed onto the stack. So that's what's happening here. So parameter 3 gets pushed before parameter 2, which gets pushed before parameter 1 because they're pushed in inverted order. So the last parameter gets pushed first. And then after that, we call the subroutine. So we call foo, and the call instruction specifically places this return address. It pushes it onto the stack. And so the return address is just a address that represents the next instruction after the call to foo. So that way when foo is done executing, the program knows where to return to continue executing in main. So that's what that is. And then to restore the machine state after foo is done executing, we would remove all of these parameters off the stack by popping them. And then we would also restore the content of EAX, ECX, and EDX by popping them off the stack. That's not shown in this diagram, but that's what would happen. And then in this diagram, the higher addresses are at the bottom and the lower addresses are at the top. So it's growing from high to low. So it's growing that way. So it's a little bit different in terms of just the way it's drawn, but it's still following the fundamental like design of the x86 stack. So it's growing from high to low. And then it's also really useful to know that parameters are always at a positive offset from a saved base pointer, whereas local variables are always at a negative offset. And that will make more sense the more we talk about things. Like when we talk more about the Cawley, it might make a bit more sense. So when main calls foo, foo is the Cawley, and foo has to do some things after it gets called. So it has to push the value of EBP, which is the base pointer, onto the stack. And then it has to copy the value of the current stack pointer into the base pointer. So what that's doing is it's saving the value of the base pointer before it's changing it. And that's to create the idea of frames, of stack frames. So that way each function has a window of memory on the stack that can be easily partitioned off in a way. So you can easily figure out what segment of the stack belongs to foo, what segment of the stack belongs to main, what segment of the stack belongs to another function, by looking at the values of these saved base pointers. The base pointers and the stack pointers are the way to kind of not border, but partition off that space. So I know that's not too clear just yet. I will try and make that a little bit more clear as we go. So that base pointer is pushed onto the stack, and then the current value of the stack pointer is put into the base pointer. So the stack pointer always points to the top of the stack. So it always points to the most recent thing that got added in memory. So when we're moving the stack pointer into the base pointer register, we're basically saying we want to store the address of the top of the stack into the base pointer and create a new frame on the stack. So we want to have a new area of memory solely devoted to foo. It'll be dedicated to foo's local variables and anything else that foo uses. So the next thing we do is we push those local variables onto the stack. And so we have to make space for them and push it onto the stack. So we push local variable 1, we push local variable 2, we push local variable 3. After pushing local variable 3, the stack pointer is pointing right here. And then the next thing that we have to do is we have to push the values of callee saved registers. So that's EBX, EDI, and ESI. So we're pushing EDI, pushing ESI. And now the stack pointer is pointing here. So now if we want to look at what's associated with foo, we just look at what's in between the stack pointer and the current base pointer. And so all of this section corresponds to foo's memory, all the stuff that we need for foo. So does that make a little bit more sense how the stack pointer and the base pointer work to kind of partition off those different stack frames, or is it still unclear? Okay, since I'm not seeing any comments and I'm not hearing anyone asking questions, I'm going to assume it's clear. So I'm going to go ahead and please let me know if I should be going faster or slower. I basically created this as a introduction, and so I made it like pretty ground level. So I may be going too slow, or I may be going too fast for some people. So let me know how the pace is. And then when foo finishes and needs to return context back to main, it will put any return, like if the foo function returns an integer, so it's telling the score of some game, and it returns an integer corresponding to that game. That return value will be stored in EAX once this subroutine is returning. And so we will then pop the values of EDI and ESI because those are callee saved registers. So we're popping those off the stack. And then any local variables that got allocated, we're going to deallocate them by popping them off the stack. So we're popping those. and then we're going to restore the old base pointer by popping that saved base pointer. So that way, it now knows that the base pointer for main is somewhere down here. So we're just restoring the caller's base pointer by popping it off the stack. And then we're returning back to the main function. We're returning back to the caller by executing what's called a ret instruction, which is return. So it will look at this return address that got stored on the stack. It will pop it off and pop it into the EIP register. So it pops it and then moves that value into the EIP register. So it's setting the instruction pointer equal to the return address. So that way the program knows to continue executing at that return address. So it can continue executing in main. So this is just a quick example of a C function and how it gets stored on the stack. So we have some function foobar with 3 parameters, 4 local variables, and then a return value here. And it's called by main. So it's pretty similar to kind of the example I was saying when I was describing everything. This diagram is actually flipped from the previous one. So this one, the high addresses are at the bottom and the low addresses are at the top. This one, it's switched. So I'm sorry for having conflicting diagrams that make it more confusing, but the stack will continue to go from high to low. But this time we're going to say the high addresses are at the top and the low addresses are at the bottom. So when we're in main, we assume everything for main is already set up. So we're going to do everything we need to do for calling foobar. So if you remember, we need to store parameters on the stack. So it's in reverse order. So we need to push C, we need to push B, and we need to push A. And these offsets are because they're all referencing based on the base pointer. And then they're all multiples of 4 because of the size of an integer. So an integer is 4 bytes. So we're just offsetting by 4 each time. So we push C, B, and A onto the stack, and then we push the return address, and then we switch into the callee, basically. So now it's foobar's turn. Foobar pushes the EBP onto the stack and then moves the stack pointer into the base pointer register. So that way the base pointer currently points there because at the time the stack pointer is pointing here as well. So at this moment, the stack pointer is pointing here. So you're just setting the base pointer to also point here because the stack pointer is going to change. And then we need to push our local variables. So we push XX, YY, ZZ, and sum. And now the stack pointer is pointing to the top of the stack, which is sum. And then we would need to push EAX. They don't show that here, but EAX would get pushed, which is this value. And then any additional saved, like callee saved registers, we would have pushed those already. So EDI and ESI, we would have pushed those already. And then we return context back to main, and then main pushes EAX, so that way it can fetch that return value, and then it pushes all of the, foobar would push all of these off the stack. It would deallocate all of these. And then also it would push that saved EBP. And then main would push EAX, and it would push the return address to set EIP, and then it would push A, B, and C to deallocate those as well. So in assembly, this is roughly what it would look like. So there's some comments in there, so you can return to the slide later and basically kind of double check the logic. But like we said, foobar, it pushes that base pointer, sets that stack pointer, sets EBP equal to the current stack pointer, because the stack pointer is going to change, and we need to set the base pointer equal to the current stack pointer before we start pushing things in the context of foobar. And then we need to make space for local variables on the stack, and then we have to push, we have to move data for XX, YY, and ZZ. Because we subtracted 16 from ESP, we don't need to use the push instruction. We can just use move instructions after that. So a push instruction allocates space and moves a value. So it's the equivalent of sub and move combined. So if we wanted to basically allocate space for multiple local variables at a time, you're more likely to see it done this way, where you just subtract a big chunk of space and then move the data over, versus doing 4 individual push instructions. But it's just dependent on the compiler and how it decides to do that, because a push instruction will resolve into a sub and a move. So this is actually the more optimized way of doing this. So then it's going to add XX, YY, and ZZ. It's going to store it in the sum. So we're just doing some arithmetic operations, and then with the add, and then we're moving the value that got stored in EAX, and we're moving it onto the stack. We're moving it into EBP minus 16. We're moving it into that space. So we're moving it into sum. And then there's more arithmetic operations for computing the final result. And then we leave the context of the subroutine. And then leave is equal to move and pop, respectively. So like it's equivalent to this combination of instructions. So in order to get to some of the other content, I'm not gonna go through every single line of this. I'm gonna let you guys look at it on your own. But yeah, you can reference this and go through and make sure you understand what the assembly instructions are doing and why they're doing it a certain way. The comments should help with that, and same with the diagram, but feel free to contact me if you have any questions on it. So now I'm gonna go into like the tools. So for static analysis, we're going to be looking at Ghidra. So I'm going to show some of the features of Ghidra, and then we're going to use it to quickly look at a binary and figure out how to crack that binary. So I'm going to stop sharing so I can pull up Ghidra, and then I'll start sharing again. And then I'm sorry again about having the screen share paused. Does anyone have any questions on the content I've talked about so far? Sorry, I'm just getting Ghidra up and running, and then, okay. Okay, so you should be able to see Ghidra right now. So right now I'm going to show you a qualification binary from Seesaw 2019. So I'm sorry if this is repetitive for some of you. I know at least one or two people have already seen this binary, so I apologize for that. I have additional binaries if you want to try your hand at other like keygens or crackmes, but this one's pretty good for kind of explaining how Ghidra works and using it for a reverse engineering challenge. So the first thing you want to do is you want to drag and drop your executable into a project that you created. And so if it recognizes the architecture, it'll pull up this little window, and it'll say what format it is, what language, and then whatever your program name is. So in this case, we're dealing with the x86 ELF binary. So let's get this going. And then this is just output of analysis. And then you'll want to open it up by double clicking it. So I'll open it up with the code browser tool. And then it says it has not been analyzed. So you want to analyze it. So click yes. And then default options are usually good. There's very rare cases when you want to mess around with any of these options. So almost always you want to just click analyze. So right now it's running its decompiler and it's analyzing the assembly to extract functions, analyze symbols, and figure out kind of what the equivalent C code should look like. So right here we have our disassembly window. So this is where we'll see our x86 assembly instructions. So,
we can't see the code browser window.
Okay, thank you. I will change the sharing. All right, now you should be able to. Do you see it?
Yeah, we can see it now.
Okay, so this central pane is the disassembly window. So you'll see x86 instructions that correspond to the program. So you can see like move, add instructions, and just as a heads up, this is x86 64-bit. So that's why you'll see RDX and RBP. Whenever you see registers with an R at the beginning, that's usually referring to x86 64-bit. So it shouldn't change our analysis too much. You guys should be able to get the general gist based on our discussion of 32-bit. It's not too different. So we have the disassembly window in the center, and we have a decompiler window on the right. So the decompiler window attempts to reconstruct the source C code from the assembly instructions. So that's really nice to be able to look at a higher level representation and not just look at the assembly. But because it's reconstructing the source code, it doesn't have the exact source code. It's not going to be exact. It's not going to be a one-to-one translation. So there's going to be some weird quirks with the decompiler, and you just have to kind of keep that in mind. Sometimes you can't trust what the decompiler shows you, and you have to rely solely on the disassembly. But most of the time it's pretty good, especially for x86. We can try and narrow our focus. So when we load in this executable, instead of just scrolling through these, like the whole binary, we can kind of focus our attentions by either looking at the functions or looking at the defined strings. So I usually look at the strings first and see if there's anything that stands out as a user-defined string. So if we look through, most of it is pretty much related to the program, like a lot of section names and libc functions. So nothing too interesting yet until we get down here. So it says, great job, the flag is what you entered. And then the flag is I'm hiding. So those definitely stand out as not just general strings that were compiled like as part of library functions. Those are, a user had to specifically type those. Those are not standard. So I want to focus in on what functions reference those strings. And the way you can do that is you can look at these cross-references. So xref refers to cross-references, and it lists what functions reference that string and at what address. So we see it's referenced by secret function and it's referenced by challenge function. So the flag is I'm hiding is referenced by secret function, and great job, the flag is what you entered is referenced by challenge function. So we can take a look at challenge function by just double clicking. So now we are in challenge function. So this is the disassembly. So if we remember what we went over, we can see a lot of things getting moved onto the stack because we're moving some data into RBP plus an offset. So this is all just things getting moved onto the stack. And if you remember the order of when things get moved, this is going to be our local variables. It's not going to be parameters because those would have already been moved before challenge function got called. So we have a lot of local variables here. And then we have some XOR operations. We have some compares, some jumps. So there's probably some sort of operations that are going on that manipulate some of that data on the stack in some way. And we could go instruction by instruction on here, but I don't want to take up too much of your time already because I'm already going over time. So we're going to look at the decompilation. So these are all the values we can see getting moved onto the stack. So the 1, 2, 1, 2, 1, 2, 1, 2. Those are all local variables that got moved onto the stack. So that is pretty easy to see. And then when we go down here, that kind of corresponds to this section. So if we look at the decompilation, we see a while loop. And it says, while this local variable is less than 8, execute everything in here, and then increment logo2 plus 1. So that is how the decompiler basically reconstructs for loops. So this is just an index. So while I is less than 8, I plus plus. That's basically what's going on here. And then this is the content of the for loop. So that's just what is going on here. And then this is where things get juicy. We need to set bvar1 to true because we want to get the great job, the flag is what you entered. This is a challenge. We want to get to this point. But in order to get to this point, we need bvar1 to be true. So we need to understand what this check is, and we need to figure it out so that way we don't trigger this. We don't want bvar1 equaling false. So we can see that it's using our parameter. So we're passing something into this challenge function. So it's a char pointer. So it's some string of text. So it's using that string of text, and then it's referencing a specific index within that string, and then getting that character. So it's getting the index at local 2C. So remember, this was our index variable. So in our for loop, that index variable will increment. So we're using that index variable to actually index into our input string. So we can see that like in the first iteration of the loop, so local 2C starts at 0. We can see that here. It'll be param1 at index 0. So we're taking that very first character in that string. And then we're casting that character to an integer. So that's what the int in parentheses is doing. Casting that to an integer, and then we're subtracting this hex. So we're subtracting 30 in hex from it. So we can right-click in the assembly window to view what its equivalent is in decimal. Convert. If you do convert, you can see what it is in decimal. So it's subtracting 48. So you can click that and it'll automatically change it, which is a really helpful feature because you're not going to want to do a lot of hex conversions by hand or using a tool. You can just use it. You can use Ghidra's conversion features directly. So it's taking the integer value of that character and it's subtracting 48 from it. And then it's, well, before I tell you what it does anyone know what this character is, what it references in a function? like what operation it's saying to do. All right, I will tell you. Oh, okay, we got someone answering in the chat. Yep, it is an XOR. So we are XORing that result with 3 and then comparing it to local 28. So we're comparing it to this, this array at the same index. So if the index is 0, we're comparing that very first integer. So we would be comparing 1. If we were looking at the second, and like the index equals 1, we'd be looking at 2. Index equals 2, looking at 1, and so on and so forth. So we're just basically iterating through this loop and comparing each character in our input sequence to the corresponding character in this array, and we're comparing them as integers. And our input is getting subtracted by 48 and getting XORed by 3. So basically, we just need to figure out what input do we need to pass to get 1, 2, 1, 2, 1, 2, 1, 2 after being subtracted by 48 and XORed by 3. So the way we can do this is we can reverse these operations. So if you know about XOR, you know that the way to undo XOR is through XOR. So if you XOR A and B and you get C, if you then XORed A and C, you would get B. So it's, you can apply it to undo a previous XOR operation, basically. So we want to know what XOR, or what 1 XORed with 3 is, and then what 2 XORed with 3 is. And then after we know that, we can add 48. And then we'll have the input string we need that will be able to go through this loop and then be equal after these operations to 1, 2, 1, 2, 1, 2, 1, 2. Does that make sense? All right. And then I already know the solution, like what 3 XORed with 1 and XORed with 2 is, and you can quickly figure it out afterwards if you wanted to do it by hand or if you wanted to do it with just an online conversion tool. But I am going to kind of spoil it for you, and I am going to tell you what it is, unless you guys really don't want me to tell you and you want to find out for yourselves. Does anyone have any qualms with me telling you what the inverse of these 2 operations are? All right, I'm not seeing any protests, so I'm gonna go ahead. But basically, after you XOR with 3 and add 48, it's actually equivalent to ASCII 2, 1, 2, 1, 2, 1, 2, 1. So it makes it nice and simple. So when you pass in the string 2, 1, 2, 1, 2, 1, 2, 1, when each character is converted to an integer, and you subtract 48 from it, and then XOR with 3, it will be 1, 2, 1, 2, 1, 2, 1, 2. So we can always check that by running the program, which I can show you, but I want to show you some other features of Ghidra first. So functions over here shows you all of the defined functions in the program, which is really useful. So you can jump straight to that challenge function by double clicking it. And we also saw when we were looking at strings, we saw that cross-reference to secret function. So if we open that up, we see it's just a really simple function that just prints the flag is hiding to the console. So it doesn't need us to reverse engineer anything. It doesn't have anything too exciting. It's just a secret function. So that's, you can navigate through the functions through there. You can also see if there's any defined classes by clicking classes. You can also look at the different sections of the executable by navigating in this program tree tab. So you can see in SymTab, you can see any defined symbols. So like we see challenge function as a defined symbol. If your binary is stripped, this section is going to be much sparser than it is in our binary. .text, you're going to see instructions. You can look at data, see if there's any defined data for you. Yeah, you can just kind of navigate through these. You can look at a function call tree, or you can look at, here, let me navigate back to the challenge function. Yeah, you can see what functions that the challenge function calls and what it's called by. So we can see incoming references main. So that means challenge function got called by main. And so we can also see that challenge function calls the puts function. So that's what the incoming references and outgoing references refers to. If we want to see that in a graphical view, we can look at function graph. So this is kind of similar to IDA Pro, how it graphs things. Come on. Sorry, I'm trying to zoom in for you guys. There we go. That. My trackpad is
Can't see the graph.
okay.
It's a different window.
Yeah, I'm gonna change my sharing settings because right now it's just bound to a single Ghidra window. I'll just share my whole desktop. All right. So the function view, it's similar to IDA's. So you can see this challenge function and it calls, it jumps to this other section of code. And it's an unconditional jump, which you can tell by the color of this arrow. This arrow is blue, so that means there's no condition associated with that jump. It's just a JMP instruction. It doesn't need to meet a condition to jump. However, these other jumps, the jump less than equal, that does have a condition. And that condition is indicated with these red and green arrows. If that condition is met, the arrow is green and it shows the next chunk of code. If that condition is not met, the arrow is red. And so you would go to this chunk of code. So it makes it easier to kind of map the control flow. And it's very similar to IDA's view, if you're familiar with IDA and how IDA's graph works. So it's just a easier way to follow the control flow of a program. There's a lot of other features, like you can use RevSync to collaborate with other people in real time. So that way you can do disassembly and like comment on the same binary across the server. So that's really nice. You can also, you can look at memory information. You can look at scripts. So the script manager is a really useful tool. So there's a bunch of built-in scripts in Ghidra. So it comes preloaded with all of these. So not all of them are going to be particularly helpful, but you can easily execute any of them by just double clicking. You can also create one of your own scripts by moving it into the script folder and then double clicking it. It supports Java and Python scripts. So this is the Java script interface, but you can also script in Python too. So that's really useful. And then I think that kind of covers everything I wanted to show with Ghidra. Then I will go back to presentation with dynamic analysis. So I will quickly show GDB. So this is the qualification binary we are looking at in Ghidra. So if we just execute it, nothing happens. But if we pass it an input string, it'll execute and it's invalid, so it won't print anything. Now if we print, or if we pass it the right string, so we figured out it was 21, 21, 21, 21. It gives us, great job, the flag is what you entered. So that's just a way we can verify. Now, if we wanted to use GDB to dynamically analyze this, we can just call GDB and then pass it the name of the program, and then it will try and load symbols. And so you can see all of the different features that GDB has with help. There's a ton. But the first thing you generally want to do if you're using GDB to run a program and you already have knowledge of what the functions are in a program, so we already know that there's this challenge function. We can just set a breakpoint at challenge function. So B challenge function will resolve that function name to its address and set a breakpoint there. And then we can run the function, and then we see it exited. Well, if we remember, we didn't pass it any input. We didn't pass it the right string. So it's going to just exit. So we need to pass it some input. So we can run it again, and we can pass it some input argument. So we can pass it something we know it's wrong. But now we see it hit our breakpoint that we set earlier. So we know we're in challenge function. So we can use the disass command, which is just short for disassembly, to see what instructions we're actually about to execute. So we know we're in this Z17 challenge function. And these are the instructions that are about to come up. We can single step through these by doing step I, and then we can disass to see where we are. So we're still moving stuff onto the stack. But we know we don't care too much about this. We really only care about that check, so we can set another breakpoint closer to that check, or we can just keep going. So now we're at this compare for the while, I think. Yeah, because there's some jump instructions. So that's basically the control flow for that while loop, which is equivalent to a for loop. So we're pretty much where we want to be, because it's going to check the index, and then we're going to have that check for our input to see if it's what it needs to be. So we can just step once more, and now we jumped back here. So now it's this is where it's doing the operations, the subtraction, the XOR, and we can check the state of our registers when we get to here. Yeah, now we can just do IR to look at our registers and see what's in EAX. So we see RAX, so that's the whole register, is equal to hex 31, but we only care about those, the lower 32 bits. But you can do a lot with GDB. You can look at the different types. You can look at symbols. Yeah, you can query like symbols. So if you know a variable name, you can see where it's located in memory with info, address, and then the name of the symbol. There is a ton you can do with GDB. GDB is also scriptable, so you can script your own like you can have your own scripts to basically do whatever you need to do. Sorry, I'm trying to check the chat because I saw a message pop up. But that's just kind of a broad overview of GDB. Basically, you're just using it to check the state of a program at a given point in time. And you can use it to figure out if you have the right inputs or not. So we know that we passed it, whatever we passed it, then subtracted 30 from it, well, hex 30, we got 1. So we passed it hex 31. All right, so that gives kind of like a broad overview of GDB. I'm not gonna walk through this entire challenge with GDB because there's still a little bit more in the presentation. I know I'm super over time and I'm sorry, but we're almost at the end. So that kind of goes over the basic tools. We also can touch on symbolic execution. So we can use symbolic execution to automate a lot of the dynamic analysis for us. So we can use symbolic execution to explore the state space of a program and basically test all input paths and program paths, so that way we can find the exact input that would satisfy our program. So we don't have to do that painful manual reverse engineering. So that program I showed you guys, we could easily script up some input to be used with a theorem prover like Z3, and then Z3 would be able to tell us what input we needed to pass to the program in order to get to that message, great, the flag is what you entered. So we wouldn't need to know like the XOR and the subtraction operations. We wouldn't need to know that we had to do those. We would just need to be able to represent the inputs as symbolic inputs and then apply constraints. So we would have to specify some constraints. We can also use Anger, which combines tools like Z3, so those theorem provers, along with symbolic execution engines and some static analysis tools to do more sophisticated analysis. So it's less user specified than, say, Z3. Anger abstracts some of that away from you and does more of the analysis. And it's very, very powerful. And then CLE is a symbolic execution engine that can be used with the solver or it can be used standalone for similar purposes. It can generate test cases for programs by representing all the inputs as symbolic, and that way you can see how many different paths there are through a program, and also what paths could potentially lead to bugs or vulnerabilities. So there's a lot of really cool applications of these kind of tools. Game hacking, so we talked about it at the beginning with game mods. The tool that is most used for that is Cheat Engine. So it comes with a lot of tools packaged inside of it, including a disassembler and a debugger. But it also has the ability to manipulate like Direct3D, DirectX, the visual assets like graphics. So that's really, really interesting and unique to Cheat Engine. And it allows you to look at these, like look at memory and scan memory while the program is running. So you can hook specific parts of memory and then modify their values while the program is running. So if you're playing a game, you can hook the program with Cheat Engine and you can modify, like, say, the number of lives you have. And so you can give yourself 10,000 lives. And it's as simple as just finding the address where the lives variable is stored and then just changing that value. And then you're done. You have a ton of lives and you can continue to play to your heart's content. And then reverse engineering, we talked about this a bit earlier, but just be careful about what you reverse engineer. Only reverse engineer things that you have explicit permission to reverse engineer and that don't have copyrights associated with them. We have two classes that are directly related to reverse engineering. We have several others that touch on reverse engineering. Malware reverse engineering is taught by Dr. Wilson, and you reverse engineer various different samples of malware that are from the wild. They are real malware samples. They're not student produced. They are heavy duty malware samples. And you figure out how they work. You write a report on it. You get to do static and dynamic analysis. You use some of the tools I mentioned. like Ollie Debug, Ghidra, IDA, and it's a really cool class. I recommend it a lot. Automated hardware and software verification focuses on the symbolic execution side of reverse engineering. So it's applying those tools to analyze larger software or hardware systems, looking for vulnerabilities. So those are two classes that touch on reverse engineering. And then these are just some additional resources, some books that I found useful, and some sites for CrackMe's that you can download. CrackMe's.one has a lot of good ones. Reversing.kr has some. CTF Time, if you look at old CTF problems, there's a bunch. And then just, if you want to get further involved and you're not already on any of our sites, here they are. And I think that pretty much covers it.